Hi guys, today we are talking about the 65s in Unit 1. This is formula writing. So up until this point, we have been talking about writing names for formulas. Today we're flipping it, and we'll be writing formulas based upon the name. So I am in the 65s. Please follow along if you're watching this video. Problem number 1 here, halfway down the page, is for sodium chloride. So whenever we want to write a formula, we have to first look up the two pieces that we have in our name. So if we find sodium on the periodic table, you'll find that it has a +1 charge. I'm going to write that right above the word sodium to remind myself what that is. Chloride, if you look that up, has a 1- charge. Okay? So now, every single compound that we create has to be neutral, meaning that its charges have to equal 0. So if I've got +1 and I've got -1 for my two options, I only need one of each when I make my formula. So if I write my formula out here, I'll just get NaCl, one of each. Okay? Now, if you think about this for a second, alright, if you consider that molecule, you'll maybe say to yourself, well, that kind of seems right as well. And the math is right, but in reality, formulas have to be reduced. Okay? So we can't write this as anything other than NaCl. Na2Cl2, while mathematically is correct, is not the appropriate formula. So that would be wrong. So if you ever get to a point where you have a formula or you write a formula and you realize that you have something that can be reduced, please reduce it, because the reduced form is the correct answer. All right, let's keep going. For the next one, we have lithium nitride. You find lithium on your periodic table. You see that it has a 1+ charge. Again, write that right above the word. You find nitrogen, or nitride if it's an ion, and you notice that it's 3-. Write that in as well. Now, we have to do some math. Okay? When we make a formula, we have to get to 0. So we've got to have the correct number of each lithium and nitrogen in our formula so that we do actually have a neutral compound when we're done. So, if I want to get to 0, I'm going to need 3 lithiums to get to 3+, and just 1 nitrogen that is 3-. 3+ added to a 3- gets you to 0. Okay? So, when we write out the formulas, we use subscripts. That tiny little 3 behind the lithium represents 3 lithiums. Okay? So we use subscripts in formulas. Let's keep going. Tin 4 bromide. Now, I could look up tin on my periodic table, but I actually don't have to. That Roman numeral right behind it, that Roman numeral 4, tells me exactly what charge tin is. So I don't have to go looking for anything. So I'm going to put 4+ above my tin. And I got to look up bromide. Find bromine. Way in the second to last column, it's a 1- charge. Again, we got to balance this thing out. We got to make a neutral compound or a neutral formula. So I'm going to need 1 tin and 4 bromides to make a compound that is a charge of 0. Just like that. The next one, number 4. Mercury 2-phosphate. Again, I don't need to look mercury up. The charge is right there. The 2 for Roman numeral means I got 2+. Phosphate. Alright, this is where it gets potentially tricky. If you ever see the second part of your name ending in ATE or ITE, you have a polyatomic ion. So phosphate is going to be on the back of your periodic table. So that's what we're looking for right there, ATE. Alright, that's a dead giveaway that you've got to flip your periodic table over. So I flip it over, I find phosphate, and when I find it, it's PO4, 3-. So the total charge of a phosphate is 3-. Again, we want our compound to be neutral, so we want to get to 0. So what we have to do is make the correct ratio of these charges. So for mercury being 2+, if I take 3 of those, I'll get to 6+. And if I take 2 phosphates, I'll get to 6-. Those cancel out, and we've got a good neutral compound. Okay, now in my formula, you'll notice that I used parentheses around the phosphate. So I enclosed that PO4 in parentheses, and then I used a little tiny subscript 2 outside of the parentheses. So what those are there for is it's to show that we have a polyatomic ion. Whenever you have a polyatomic ion in a formula, you have to show that that piece stays together. So the parentheses will help us kind of visually see that we have something more than just individual elements. We've got a polyatomic ion. Let's keep going. Chromium 3 carbonates. The Roman numeral tells me I got a 3+. Carbonate, ATE. That's a dead giveaway. I've got a polyatomic ion. I'm going to flip it over, find my carbonate. I find CO3 2-. So my carbonate has a 2- charge. And again, I got to balance this thing out. So I'm going to take 2 chromiums and 3 carbonates. That'll give me 6+ and 6-. My total formula will be 0. Okay, so once again, carbonate's a polyatomic ion. I need to enclose that within the parentheses, and then the tiny little 3 on the outside of that is telling me that I've got 3 carbonates. Number 6, aluminum cyanide. We look up aluminum on our periodic table, and we should find that it is a 3 positive charge. We look up cyanide, okay, and this one might be tough to find. Now, cyanide ends in IDE, but it is a polyatomic ion. This is one of those exceptions. So normally I told you to look for 8s and ites, but cyanide's on the back of your periodic table. So you find cyanide, and you'll notice that it has a 1- charge. So once again, I got to make a neutral compound. So what I have to do is I need to take 1 aluminum and 3 cyanides to make this total charge 0. Okay, so that's the correct answer. Now, if you did it this way, like that, that is incorrect. All right? When you write it out like this, what that tells me is that you have 1 aluminum, 1 carbon, and 3 nitrogens. When in reality, what we need is 1 aluminum, 3 carbons, and 3 nitrogens. So that polyatomic ion, that cyanide, CN, it stays together. We have to show that if we have 3 total, that means we have both 3 carbons and 3 nitrogens, and the parentheses help us do that. So that lower answer there is incorrect. Let's keep going. Number 7, ammonium oxalate. This one has 2 polyatomic ions. Ammonium is the top polyatomic ion on your chart. It's the only one with a positive charge. And it has a positive 1 charge, so I'm going to write that above. And oxalate is C2O4, and it has a 2- charge. All right, so now we have 2 polyatomic ions. We're going to need some parentheses in this problem. So ammonium, we're going to need 2 of those things. So I'm going to start my formula with some parentheses. I'll close those and put a little 2 to represent that I have 2 total ammoniums. Oxalate, I only need 1 of them. So the way I'll write that is without parentheses. Now, the rule of thumb is if you only have 1 of a polyatomic ion, you don't need parentheses. But if you have more than 1, you have to put it in parentheses and then use a little subscript to show how many you have. Okay? Now, it's early on in the year, so if you write this formula like this, that's okay. It's not technically correct, and you wouldn't see it in a textbook written like that. But if you want to organize it just for the time being early on to show that those are both polyatomic ions, that's perfectly fine. We're going to have you get rid of that habit pretty quickly, but while we're learning, that's okay if you want to put both of them in parentheses. One more, 8-dinitrogen tetrafluoride. This is a covalent compound, and you can tell it's covalent based upon those prefixes. So you see the prefix di, you see the prefix tetra, and those are telling us basically how many we have. So when we write a formula for a covalent compound, it's really, really simple. You read what it is, and you simply write it down. Dinitrogen means 2 nitrogens. tetrafluoride means 4 fluorines. So all our formula is going to end up being is this. And we're done. So, hopefully this video was helpful. If you do need some more help, find Mr. Stradler or myself. We are always more than willing to help you out on these homework sheets. Thank you.